Hi, my name is Paul Fisher, and I'll be talking today about MediapH and why it's important in terms of plant health and nutrition. If we look at a solution of water, H2O, then water will dissociate into H+, or protons or hydrogen ions, and OH-, or hydroxyl ions. Now when we have a neutral pH, concentration of OH- and H+ is equal, and we have a pH of 7. When we have an acidic solution, the pH is a small number below 7. So for example, if we had a pH of 5, we would have an acidic solution where we have a higher concentration of protons, H+, than we do of OH-. If we have a pH of, for example, 9, we have a basic solution with more OH- than H+. Now in a solution we said that a neutral state was a pH of 7. In container media, our average target pH is around 5.8 to 6.2. This graph shows the frequency distribution from about 12,000 different samples of container media that was sent to commercial testing labs. You can see that the average is around the target of 5.8 to 6.2. There are about 10% of the samples that were very acidic below pH 5 or were very basic above pH 7. Now these out-of-range pHs are important in terms of plant nutrition and health. In this graph we have an increasing range of MediapH from 4.5 on the left up to 7.5 on the right. And this was an experiment that was run back in the early 80s using a media with peat and bark ash. The thickness of the bars represents how much of the soluble nutrient was measured in the experiment at each pH level. If we look at how sensitive different nutrients are to the pH, take examples of nitrogen and potassium, whose solubility is not very much affected by the pH. So uptake of those nutrients is not really affected by the pH of the substrate. In contrast, the pH, as pH increases, phosphorus solubility goes down. And if we look at calcium and magnesium in this graph, it's somewhat misleading. The solubility of those nutrients actually goes down, but the amount of calcium and magnesium that were measured in the experiment went up with increasing pH. Why was that? Because in the experiment they had increasing pH levels in the media by adding more and more lime, which contained calcium and magnesium. So it's very common at high pH that you'll have high calcium and magnesium levels in the growing media. It's not because they're really more soluble, it's typically because more lime was present in the media. Sulfur, which was not measured in the study, is not very pH sensitive. Iron, manganese, zinc, copper and boron, these micronutrients, their solubility goes down as pH increases. And molybdenum, which was not measured in the trial, its solubility goes up with increasing pH. When we have out-of-range pHs, then there are certain nutrients that typically cause problems. When pH is low, phosphorus can be leached out of the media. When pH is high, phosphorus solubility can be reduced. Similarly with micronutrients, iron, manganese, zinc, boron and copper, at low pH you can run into toxicities, especially of iron and manganese. At high pH you can run into deficiencies, lack of nutrients being taken up, especially for iron, manganese and boron. There's a petunia, which is a plant species that is not very efficient at taking up iron when pH becomes high. So here is a healthy leaf growing at pH 6. Here is the start of iron deficiency symptoms, pH 7. See the interveinal chlorosis, the yellowing between the veins, and eventually completely white with severe iron deficiency, and the growing point can actually die. In this experiment that we ran with impatiens, we had increasing levels of pH with increasing lime rates in a peat perlite medium, and as you can see, the amount of soluble iron in the growing media decreased as pH went up. The amount of iron in the leaf tissue went down, as pH went up. And also the chlorophyll, which is the green pigment that makes leaves green, also went down at a high pH. Here are the plants from that experiment. You can see that they're green from range 4.4 to 6, but were yellow at pH 7 because of iron deficiency. In this blog series, we're going to talk a lot more about aspects of, for example, selection of different forms of micronutrients. In this experiment, we had iron in the form of iron EDTA, a certain chelate whose solubility goes down above pH about 6.5. That's why we saw chlorophyll at that highest pH treatment. Here's a seed geranium, which differs from the petunia in that it's very iron efficient, takes up iron and manganese very easily when pH is low, in this case around pH 5. And you can see the speckling, necrosis around the edge of the leaf, and finally leaf death, especially in older leaves as the plant accumulates excess iron and manganese. You can see those same plants here, pH 4.3 severe iron manganese toxicity, pH 7.5 some iron deficiency starting to set in, but a healthy plant, pH 6.3. Now in this series we're going to cover a lot of different details about plant nutrition, but I guess probably at this stage the important thing is to have an overview and to recognize that there are several factors that tend to raise pH, are basic, such as nitrate, nitrogen, lime, and alkalinity in the water, and there are certain acidic factors that will tend to drop pH, such as ammonium nitrogen, media components such as peat and bark, and certain plant species such as geraniums.